In this clip, we will address the self-assembly of lipids and in particular the formation of vesicles, which are the main compartments made up in a cell. Our surprising result will be that the mechanics is governing typical sizes that also occur in nature. Let's first have a look into some experimental results. To the left you see electron microscopy images of vesicles. You see that the vesicle is empty on the inside and is only surrounded by a very thin membrane, where the thickness of the membrane is in the order of a few nanometers, between 5 and 7. If you take even a closer look to these images, you see that the membrane itself, so the 5 nanometer membrane, is not homogeneous, but there's a dense outer layer on both sides and a somewhat less dense inner side, described by the lipid head groups and the lipid side chains, respectively. To the right, you see a more pictorial way how vesicles are formed. So it's a lipid bilayer, a flat lipid bilayer, which is bent into a spherical structure which is closed. So there's an inside and there's an outside, and both are separated by a very thin membrane. Now, if you do experiments, you can look on what are the typical sizes that you will find in a cell. And what you will find is that the typical size of a vesicle in a cell has a diameter of 25 nanometer. So the aim of this clip is to understand why there is the 25 nanometer limit in sizes of vesicles. It maybe comes to a surprise that this size is dictated by mechanics. Now, there has been an extensive theory on the mechanics of thin shells, and in particular Canham and Helfrich made up a whole theory of bilayer shells with the aim to understand the typical shapes of the red blood cells. But we only are concerned here with the shape of the vesicles. So we're interested now in the energetics of bending a thin elastic sheet. Now, we know from a sheet, an elastic sheet, that if we apply a force or a tension on two sides, it will extend. Hence, also bending will need some energy. And the reason is that by bending a very thin sheet, the top of the bend will have to expand, whereas on the bottom there's compression. Now, to make this a little bit more quantitative, let's assume we have a sheet of thickness d, small d, and that we bend with a radius of curvature, capital R. Now, if we take this sheet and just roll it up into a circular structure, then the outer part of the sheet has a length of 2 pi r plus d, whereas the inner part has a length of 2 pi r. So there's a length difference in the outside and the inside. Now, in order to look on how much difference is on a small stretch ds on the membrane, there we see that the length difference, delta s, is given by, well, the 2 pi r plus d minus 2 pi r times ds divided by 2 pi r, which is a total circle. Now, doing the product here, we find that delta s is equal to d divided by r times ds. Now, our model here was a 1D model. So we bent, let's say, a line into a circle. But likewise, we can do this also in 2 dimensions. So we bend a sheet into a sphere. Then the stretch ds will change into a small patch on the surface, dA. And in order to bend a thin sheet, and thin means that the bending, so the thickness is much smaller than the radius of itself, we will need some energy to do this. So we ask how much energy dE will be needed to bend a small patch of a surface into this spherical structure. So the easiest way to get a grip on here is that we use the definition that d divided by r is a small number, and then do a Taylor expansion in d divided by r. And we come up with a first order term, k1 times d divided by r, plus k2 times d divided by r to the power 2, plus higher order terms in d divided by r. Now what we right away can say is that actually the first term vanishes. It doesn't matter for the energy whether I bend it upward or downward, both energies should be the same. Hence the first term has to be 0 and only the even terms in d divided by r will play a role. Hence from the Taylor expansion we obtain an expression for the energy to bend a small patch dA, and that is dE is equal to kappa half times 2 divided by r to the power 2, in which kappa is the bending modulus that contains, for example, the thickness of the sheet and also the K2, which is related to the Young's modulus of the system. Now, what you actually see here is nothing else like Hooke's law. So the energy is proportional to the change of an area. Now, let's try to make up a very simple-minded model on the energy that is required to bend the lipid membrane. First, we start out with lipids which are just lying on top of a flat water surface. Now, in the next step, what we do is we bend this water surface and make a small bubble. Now, at the very neck, what will occur is that the hydrophobic side chains will touch the water. And hence there will be a hydrophobic penalty because of this interaction. Now, in the beginning, we made an estimation of the energy involved, and we found that this hydrophobic penalty, sigma, is given by 2 times 10 to the power 17 kBt per square micron. Now, in terms of the bending energy E bend then is 2 times kappa divided by the area, which in this case we just assume is the length of the tail squared. And that has to be equal to this hydrophobic penalty that we just described. Now, from there we can now estimate kappa. So kappa is equal to L squared tail half times sigma, where L squared, where the typical length of these hydrophobic tails is in the order of 2 nanometer. Hence, the bending energy that we obtain in this very simple-minded way is 19 kBt. Now let's put our model and also the numbers, the rough numbers that we now estimated, together, with the aim to understand why vesicles are 20 nanometer in size. Let's first have a look on the bending energy. So how much energy is needed to bend a membrane into a sphere? Now, we derived the differential form saying that the bending energy is equal to 2 times kappa divided by r squared dA. But in order to calculate the full energy, we just have to integrate on the sphere. Now, assume that kappa and also the radius of the sphere is constant. These two factors we just take out of the integration, and we obtain that the energy is equal to 2 times gamma divided by r squared times the integral on the surface of a sphere, being 4 pi r squared. Hence, the total energy to bend a sheet into a sphere is given by 8 pi kappa, the bending modulus of the sheet. Now, a very surprising result. The energy that is required to bend a thin sheet into a spherical object does not depend on the size. Whether I bend it to a very big vesicle or to a very small vesicle, the energy is always constant. Also, if we now fill in the numbers, we find that with the kappa equals to 19 kBt, the total energy to bend a bilayer into a vesicle or into a spherical structure costs 400 kT, which is a tremendous amount of energy that would be required. So we might wonder, why do vesicles form at all? So let's suppose they don't fold and that these membranes still self-organize, but we just have a flat patches floating in a solution. Now, to keep things simple, we just assume that we open a vesicle and that forms just a round patch of lipid membrane. Yet on the side of the lipid membrane, or of this patch, there will be hydrophobic interactions, which is a penalty energy that is required to overcome. Now, for that case, the energy, the hydrophobic energy of the patch is given by the circumference, which is 2 pi r times 2, because we have a lipid bilayer, times the line tension that describes this interaction energy. Now, again, in the beginning of the lecture, we looked on the line tension and we found there that it was 3000 kT per micron. So now we have to compare the energy that is required to bend a vesicle and compare it to this line tension and the patch energy that we just described. So we found that the bending energy is independent of the radius. It's 8 pi kappa. And that has to be smaller than the line tension energy that we describe here, which is 4 pi r lambda. Now, solving for the radius, we obtain that r has to be smaller than 2 kappa divided by lambda, being about 20 nanometer for the values that we calculated. Hence, what we found that this very simple mechanical model tells us that there is a minimum size of vesicles, and that is governed by the bending stiffness of the membrane. Now, as a take-home message of today's lecture, we wondered how cells can be organized into these very complex systems, and we found that the cellular organization is driven by self-assembly. We looked into the formation of, in particular, vesicles and membranes, and we found that this is governed by the hydrophobic effect, which describes the entropy loss of the solvent molecules, the water molecules, in the neighborhood of oils. We found, in order that self-assembly to occur, that the concentration of the molecules, so the amphiphiles, forming the self-organized structures has to be larger than the critical micelle concentration. Further, we found that bilayers form closed structures. Those are called vesicles. The formation of vesicles is governed by the mechanical properties of membranes. Bending energy, or the change in the bending energy, on a small patch, dA, is thereby given by kappa half times 1 divided by r1 plus 1 divided by r2 squared, where r is the typical radius of curvature. Now, in this complete formulation, which we didn't use in our description, we assumed that vesicles or membranes can not only be curved into a spherical structure, but that there are two radius of curvature that have to be considered. Now, from these considerations, we simply could estimate that the smallest vesicle size is 20 nanometer, which actually has been experimentally found.